Ladies and gentlemen, thank you for inviting us to participate in the third International Conference on Sustainable Futures, Environmental, Technological, Social and Economic Matters 2022. We are honored to share with you our research paper on reliability indicator based on assessment entropy of mining building and structure elements. And before our presentation starts, I'd like to introduce our teammates of Kryvyi National University from Ukraine under the leadership of Doctor of Technical Sciences, Associate Research Dmytro Brovko, two candidates of Technical Sciences, Associate Professors Vasily Khvorost and Vladimir Kononenko, and Associate Research Vitalina Tyshchenko. Here we go. This paper is devoted to the analysis of methodological supportive work in addressing safe operation of mining buildings and structures in view of insufficient information in their operation and inspection. Industrial production, on the one hand, provides economic development of the state and vital activity of society. On the other hand, is a source of potential danger. According to the data of the State Emergency Service of Ukraine, the statistic of emergencies due to sudden destruction of buildings for 2014-2021 is represented in the table. Analysis of the mining facilities of Khvorost enterprises shows an uneven increase in the unsuitability of their operation. One of the reasons for the situation is that the mathematical and physical models used do not fully reflect the real process. Therefore, safe operation of industrial buildings and structures should be ensured by developing and implementing the safety management. This concept establishes safe resource object in appropriate ways and measures to ensure operation reliability. Analysis of the inspections materials indicates occurrence of defects caused by accumulation of damages at all stages of functioning: manufacturing, transportation, storage, installation, and operation. In the first 35-38 years, we observe uniform development of defects and null elements without occurrence of progressive jumps. Further, by the 57th year of operation, we observe a stepwise development of defectiveness in the main structure groups of elements. After 60 years, there is a sharp increase. Three groups of elements are distinguished: headframe, underframe, jib, and bench. Particularly surprising the elements of the jib. This may be due to the wrong attitude to the importance of this group in operation. The analysis confirms that the reliability of buildings and structures elements of the surface complex depends on the magnitude of imagined defects and the time of the occurrence. In most cases, the family of power loss distribution allows you to reasonably determine the technical condition of the object in the whole system. On the basis of the headframe Yubilina mine, we model the strength characteristic of industrial objects on the mine surface and calculated them through the design and computational SCAD complex. The complex realizes finite element modeling of statistic dynamic calculation schemes, checking stability, selects unfavorable combinations efforts, and checks bearing capacity of steel structures. The calculation is based on the finite element method using the nodes of the calculation scheme as the main unknown displacement and rotations. In complex systems, the failure of even a single element can lead to extremely serious consequences. The reliability calculations based on the fact that each element has a certain strength in relation to the loads. The usual design method applies very arbitrary coefficients such as safety factor and safety margin and doesn't allow to judge the probability of an element failure. It is clear that the conventional deterministic design approach is not satisfactory in terms of reliability analysis. Thus, another design methodology is needed that supports the probabilistic nature of design parameters and evaluates the reliability of element of the design stage. In this case, the measure of reliability is understood as the probability that the maximum stress arising under the load doesn't exceed the bearing capacity of the element. In general case, it is represented by expression 2. Using this expression, it is possible to calculate the probability of failure-free operation of the element for various combinations of distribution laws of the bearing capacity and load. For example, in the case of normal distribution of load and bearing capacity, the probability of failure-free operation is determined by expression 3. Graphics for this dependencies data we can see on the next slide. In real situations, bearing capacity of element and its durability depend on geometrical dimensions, material characteristics, and influencing factors. If geometrical parameters are deterministic quantities, the material characteristics of the element are random quantities with given distribution laws. The manifestation and intensity of external factors in most cases have a dual stochastic character, which doesn't allow to describe both theoretically and empirically. This slide shows the parameters of distribution functions, which describe the stress state of structural elements, changing both in height of the object, left part of the figure, and in time under the action of various factors, for example corrosion, right part of the figure, and have a probabilistic nature. In our work to assess the survivability of the element taking into account the probabilistic and priori specified characteristics, it is proposed to use the KULLBACK-LEIBLER distance. The KULLBACK-LEIBLER distance, or relative entropy, is an asymmetric measure of the distance from each other of two probability distributions defined on the general space of elementary events, and is defined from the expression. In the course of this research, we obtained the calculated values of the KULLBACK-LEIBLER divergence to estimate the survivability of the structure elements. So look at the table, please. From the table, the KULLBACK-LEIBLER divergence is an inverse dependence on the value of corrosion wear of structure elements. Thus, you can see that the maximum level of the parameter corresponds to the calculated design value, and the minimum parameter refers to the emergency condition of the structure elements. This slide shows a graphic on the change in the KULLBACK-LEIBLER divergence under the corrosion in the elements. The shift in the distribution of stresses in elements occurs as a consequence corrosion, which decreases the cross-section of the element and consequently decreases the ultimate strength. This leads to a decrease in distance between the laws of distributions and a decrease in the residual strength of the element and the system as a whole. To sum up, for the first time we developed the theoretical apparatus of technical diagnostics based on the probabilistic statistical methods. We included the base methods of statistical solutions, the concept of theory information to determine an accurate technical state, reliability, and wear of structures and structure elements. Moreover, we propose an analysis algorithm without a strict binding to a specific distribution law. Also, we calculated the KULLBACK-LEIBLER divergence in order to assess the survivability of structure elements. Thank you for your attention.